The world of computing is on the cusp of a revolution. We are witnessing the dawn of a new era, one that promises to reshape the landscape of technology as we know it. Traditional computers with their separate processing and memory units are reaching their limits. The architecture that has served us well for decades is now struggling to keep up with the exponential growth in data and the increasing complexity of tasks. This architecture, known as the von Neumann architecture, struggles with the massive data demands of modern artificial intelligence. The bottleneck created by the separation of processing and memory units is becoming more pronounced, leading to inefficiencies and slower performance. A new approach is needed, one that draws inspiration from the most efficient computer we know, the human brain. The brain's ability to process vast amounts of information quickly and efficiently is unparalleled, and it offers a blueprint for the future of computing. This is where neuromorphic computing comes in. Neuromorphic computing aims to mimic the structure and function of the brain, creating systems that can process information in a more natural and efficient manner. Neuromorphic computing aims to mimic the structure and function of the brain. By emulating the brain's neural networks, these systems can perform complex computations with greater speed and lower power consumption. It uses artificial neurons and synapses to process information in a way that is more analogous to biological systems. This approach allows for more efficient data processing and opens up new possibilities for artificial intelligence. This approach has the potential to overcome the limitations of traditional computing and unlock new levels of AI performance. By leveraging the principles of neuromorphic computing, we can create AI systems that are more powerful, more adaptable, and more capable of solving complex problems. Imagine AI systems that can learn more efficiently, adapt to new situations, and solve complex problems with human-like intelligence. These systems could revolutionize industries, from healthcare to finance, and transform the way we live and work. This is the promise of neuromorphic computing. It represents a significant leap forward in our quest to create machines that can think and learn like humans. It's a field brimming with potential, offering a glimpse into a future where AI becomes more powerful, more efficient, and more integrated into our lives. The possibilities are endless, and the impact on society could be profound. Let's delve deeper into the core concepts and recent advancements driving this exciting field forward. Join us as we explore the cutting-edge research and groundbreaking innovations that are paving the way for the next generation of computing. Traditional computers process information sequentially, following a step-by-step approach to execute tasks. They move data back and forth between the processor and memory, which can be time-consuming and inefficient. This constant shuttling of data consumes a significant amount of energy and creates a bottleneck known as the von Neumann bottleneck. This bottleneck limits the speed and efficiency of traditional computing systems. The human brain, on the other hand, processes information in a massively parallel and distributed manner. Unlike traditional computers, the brain can handle multiple tasks simultaneously. Billions of neurons, connected by trillions of synapses, work together simultaneously to process and store information. This interconnected network allows for rapid communication and processing. This parallel architecture allows the brain to perform complex tasks efficiently, using remarkably low power. The brain's ability to manage such tasks with minimal energy is a key inspiration for new computing technologies. Neuromorphic computing draws inspiration from this biological blueprint. By mimicking the brain's structure, these systems aim to achieve similar levels of efficiency and adaptability. Instead of separate processing and memory units, neuromorphic chips integrate these functions, mimicking the brain's architecture. This integration reduces the need for data to travel back and forth, enhancing speed and efficiency. This integration enables faster processing, lower power consumption, and the ability to learn and adapt over time. Neuromorphic chips represent a significant step forward in computing technology, offering a promising future where machines can operate more like the human brain. One of the key enabling technologies for neuromorphic computing is the memory store. This tiny yet powerful component is revolutionizing the way we think about memory and processing in electronic devices. A memory store is a type of electronic component that can remember the amount of charge that has flowed through it, acting as a non-volatile memory. This means it retains information even when the power is turned off. Much like a synapse in the brain remembers the strength of a connection, a memory store can adjust its resistance based on the history of voltage and current. effectively mimicking the way synapses strengthen or weaken over time. This ability to store information at the same location where it is processed makes memory stores ideal building blocks for artificial synapses. They can handle both data storage and processing simultaneously, which is a significant departure from traditional computing architectures. Memory stores offer several advantages over traditional transistors used in memory devices. They are not only more efficient but also more versatile in their applications. They are smaller, faster, and more energy efficient, which makes them particularly suitable for the next generation of computing devices. This efficiency allows for the creation of dense and efficient neuromorphic chips, which can mimic the neural networks found in the human brain. Imagine millions or even billions of these tiny memory stores interconnected on a chip, forming a network of artificial neurons and synapses. This could lead to breakthroughs in artificial intelligence, making machines that can learn and adapt in ways similar to the human brain. The integration of processing and memory in neuromorphic chips leads to a paradigm shift known as in-memory computing. In traditional computers, data is constantly moved between memory and the processor, creating a bottleneck that limits speed and efficiency. In-memory computing eliminates this bottleneck by performing computations directly within the memory itself. This approach is particularly beneficial for AI applications, which often involve processing massive datasets. By performing computations directly on the data where it is stored, in-memory computing significantly reduces the energy required and accelerates processing speeds. This paradigm shift is crucial for enabling the development of powerful and efficient neuromorphic systems. Section 5. Collaborative strides and recent breakthroughs. The field of neuromorphic computing is rapidly advancing, fueled by collaborative efforts between academia, industry, and government institutions. Research initiatives like Thor, the Neuromorphic Commons, a collaboration involving the University of Texas at San Antonio, UC San Diego, and other institutions, are driving innovation and fostering the development of open-source tools and resources. Recent breakthroughs, such as the publication of neuromorphic computing at scale in the prestigious journal, highlight the significant progress being made in scaling up this technology. These advancements are paving the way for the development of larger, more complex, and more capable neuromorphic systems. Section 6. Practical applications, from healthcare to smart cities. The potential applications of neuromorphic computing are vast and span across various industries. In healthcare, imagine wearable devices with neuromorphic chips that can analyze real-time health data to detect anomalies and provide personalized health insights. Smart cities could leverage neuromorphic systems to optimize traffic flow, manage energy consumption, and enhance public safety. Scientific computing stands to benefit immensely from neuromorphic computing. Complex simulations such as those used in climate modeling or drug discovery could be performed with unprecedented speed and efficiency, accelerating scientific breakthroughs. Section 7. Challenges on the path to wider adoption. While the potential of neuromorphic computing is immense, several challenges need to be addressed before it becomes widely adopted. One key challenge is the lack of standardized benchmark datasets and evaluation metrics. This makes it difficult to compare different neuromorphic architectures and algorithms objectively. Another challenge is the need for more user-friendly programming languages and tools. The development of open-source frameworks and libraries will be crucial for lowering the barrier to entry and encouraging wider participation from the AI community. Section 8. Shaping the future of artificial intelligence. Neuromorphic computing has the potential to revolutionize the field of artificial intelligence. By mimicking the brain's efficiency and adaptability, neuromorphic systems can overcome the limitations of traditional computing and unlock new levels of AI performance. This technology will power a future where AI is more integrated, more intuitive, and more impactful in our lives. The journey ahead is filled with exciting possibilities. As research progresses and these technologies mature, we can expect to see neuromorphic computing playing an increasingly prominent role in shaping the future of AI. Section 9. Join the neuromorphic revolution. The world of computing is on the brink of a paradigm shift, and neuromorphic computing is at the forefront of this revolution. To stay updated on the latest developments and breakthroughs in this exciting field, be sure to subscribe to this channel and share this video with your network. Let's explore the future of AI together.